a paper or an article on polynomials of unbounded positive self-adjoint operators. And my co-authors, who are my supervisors actually, were Professor Justus Mille, Dr. Lucy Chikamai, and Professor Shem Aywa, all from Kibabii University. Now, this will be the overview of my presentation. I'll be defining some terms, then go to background information, then statement of the problem, literature review, some preliminary concepts and inevitability of operators, then look at the polynomial of operators, and finally, some key references. Now, first, I'll define some few terms, just the general terms, so that we can move together. The operators that I'm talking about are just transformation. Transformation is something like a rotation, like a shear, a slide. Now they'll be acting on a Hilbert space. A Hilbert space is an example of an XY plane. Now, I want a space in where I can measure angle, I can measure length, or what I call norm, and the space is convergent, is complete. That means if I take a sequence of convergent spaces, then they converge in the same space, then that's the best space that I'll be working on. That's what we call a Hilbert space, an inner product space in which every convergent sequence will converge in the same space. And my space will be complex valued space because I want my field to be complex valued so that I can have a richer area to cover. And second, when I look at these operators, I'll be having bounded operators and unbounded operators. When I talk about bounded, I mean the image of these operators have some definite length, or can be they are unbounded above. They're bounded above by some big element in the real space. And not okay, yes, in the real space. And when I say they are unbounded, then they are defined on a small Hilbert, on a subspace of the Hilbert space, and that's typically because of the closed graph theorem that an unbounded operator cannot be defined on the whole Hilbert space. And when I say they're positive when, okay, let me just hide something here. They are positive when the numerical range is more than 0, and strictly positive when the numerical range is strictly more than 0. Of course, I'm taking element x from the domain of that operator. Now, the background of the information. I don't know where to put this so that I can be able to I want to hide it so that it cannot keep on. Okay, I don't know how I can do this. Okay, let me just put it on the side. Maybe I hope it will work. Okay, the unbounded operators are the operators that were defined to generally describe what differential operators are. And these differential operators have a lot of application in quantum mechanics, the study of mostly the study of particles in atoms, in molecules, and in many body systems. Now, these operators, these particles, of course, they vibrate, they move around, generate heat, and all that. And that motion, that means that the position of these particles, the momentum, the spin, can be described by what we call the operators. And these operators are unbounded self-adjoint operators. That's why you are interested in looking at unbounded self-adjoint operators. Why? The observables of these operators are actually self-adjoint operators. Now, the self-adjoint operators are densely defined. That by that I mean that the closure of the domain of the operator is equal to the whole space. Therefore, the idea of denseness is very important in our study, and because it helps us to define the adjoint of the operator. And now, when we have the operators self-adjoint being just bounded, then the adjoint of that operator will be equal to the adjoint of the individual operators. And since that self-adjoint, that actually equal to E plus F. That's the case when they're bounded. But when they're unbounded, this is not the case. We have equation 2 that the adjoint of the sum of the operators is just an extension of the individual adjoint. And this is because of denseness, because the operators E and F are densely defined. And that's why it becomes very difficult for one to define the polynomial of operators being self-adjoint. You want the polynomial to be self-adjoint so that the sum of the terms are adjoint, are self-adjoint. And now because of this equation 2, there is that hindrance when it comes to unbounded self-adjoint operators. And that was the problem, that was the gap. Therefore, statement of the problem that the polynomials of an unbounded self-adjoint operators are not necessarily self-adjoint because the sum of the operators may not be densely defined. And now when the sum is not densely defined, then of course it's obvious that they will not be a self-adjoint operators. But now there have been some, our attempt to solve the problem is use the result by Motard, who is a professor, of course, in Algeria. He came up with the result that the sum of two densely defined and bounded self-adjoint operators can be self-adjoint, of course, based on some condition. They can be actually self-adjoint operators. And that was our main idea. Therefore, we just try to extend this from sum to the polynomial. And therefore, we are going to consider a small category of unbounded operators, in this case, the positive unbounded operators, which are actually invertible. Invertible unbounded self-adjoint operators are actually positive. So some of them are positive. Therefore, we're going to look at that category so that we can define the polynomial of these positive unbounded self-adjoint operators. And therefore, our goal is to form a polynomial, which of course didn't exist, of unbounded positive self-adjoint operators. The importance of the study, as I've just told you, it has this concept of polynomials or unbounded self-adjoint operators has a lot of application in mathematical methods for quantum mechanics, and therefore it will ease the idea of working with the operators in that space. And of course, we know also polynomials are used in approximations of continuous function. Therefore, we can use also such operators to estimate continuous functions of operators. Now, this has been done some time back, of course, but it was done for bounded operators, bounded self-adjoint operators. It has been done by a number of scholars, just to mention a few: Rodman, Roman, and Martin. They did this. They came up with the polynomial of bounded operators. Of course, there are very many, of course. You can read this from very many books, from very many books, but that was case for the case of bounded operators. But for unbounded, that nothing has been done about it. But this researcher, Motard, came up with a result that actually, based on some conditions, we can come up with the sum of unbounded self-adjoint operators being self-adjoint. But of course, his case was somehow broader. He did it for the case of unbounded normal operators, which is a bigger class of self-adjoint operators. Therefore, for our case, we simply singled out as a weaker result of that, which is unbounded self-adjoint operators. Therefore, we are going to try to define polynomials of unbounded operators, unbounded self-adjoint operators for our case, and that was the gap from the literature. Therefore, the preliminary, we have the operator F, which is unbounded self-adjoint operator. And now we want to come up with a polynomial in terms of this operator. Therefore, we are actually summing the AKFK, equation 3, AKFK, where AK is just the coefficient, which is can be from our field, can be real or can be can be complex valued function or simply a complex valued number. And FKs are powers of this unbounded self-adjoint operator. And by definition, the domain of this polynomial is actually the domain of the highest possible power, which is actually the smallest domain for all the powers. In that case, when the degree of the polynomial is n. And to define the powers of these operators of operator f, that is fk, we want to define it. We define it recursively. That means f will be acting on f power k negative 1. Now, this is the result which we relied all to come up with a polynomial, that if we have the operators e and f being unbounded self-adjoint operators, and f being invertible, of course, commute with each other. By saying commutativity is like when the action of one operator on another is equal to the action of the other operator acting on the first operator. That's EF is equal to FE. If that is satisfied, and if also the domain of the product operator EF inverse is contained in the domain of F, then the operator E plus F will be self-adjoint. That means the adjoint of E plus F adjoint will be E plus F. And that will be self-adjoint defined on the domain of E. That was the result by Mortale. That's why we are going to come up with an extension of this result. The first thing we want to set up the condition, and this will be using the spectral mapping theorem that says so long as F is an abundant operator, and we can get a continuous function from the set of the spectrum of F to the complex valued function. If this is continuous, then the spectrum of the function of F will be equal to the closure of the function of the spectrum of F. And since unbounded self-adjoint operators are closed, why? Because the operator is equal to the adjoint, and adjoint operator is always closed. Therefore, the self-adjoint operators are closed. Closed operators have closed spectrum. Therefore, the closure equation 4, the closure of the function g of the spectrum of F is closed. Therefore, it's just equal to the set itself. Therefore, we drop this closure and simply say that the spectrum of G, the spectrum of the function of F is equal to the function of the spectrum of F. Now, next things about invertibility, we want to set a condition on when the function is invertible, and this is just in public domain, that when 0 is not an element in the spectrum of an operator, then that function is not is invertible. Therefore, we want to set a condition. If that is true, then can we set a condition for a power of F? Yes. We're using the spectral mapping theorem. You can see that Fn is just a function of F. That means it's just F power n. Therefore, we can apply that since 0 is not in the spectrum, is not in the spectrum of F. Therefore, 0 will not be in the spectrum of the will not be in the spectrum of the function of GF. And that simply implies what? That since our GF is now our F power n, this 0 will not be in the spectrum of F power n, and therefore Fn is invertible, only provided that F is invertible. Therefore, our condition that we want our unbounded operator to be invertible, so that our powers will also be invertible. And next, we are looking at the polynomial Fn 3, equation 3, polynomial, the polynomial of Fn, and we want this polynomial to be self-adjoint operator. And our approach is that we want each and every term to be self-adjoint. Therefore, based on that, we can now come up with a condition on which we can say what are the coefficients of each and every term. Therefore, we want this term AK, FK to be self-adjoint. Then when we apply adjoint there, then we'll get that equation 5. Of course, the conjugate of AK and the multiplied by the adjoint of FK. And since this, we can commute this property of powers and adjoint, we come up with the second, the third part of the equation. And since F is self-adjoint, of course, you'll drop that adjoint, you simply have the conjugate of A closure multiplied by FK. And now, if you want this to be self-adjoint, then we have to drop this conjugate on AK, and we only drop it if and only if the AK, the conjugate of AK is equal to the AK itself. And that means what? The AK is simply a real number. Therefore, we come up with the result that first, a polynomial will be defined on the set of real numbers. 2, we want to establish the idea of commutativity of these operators, because we'll be working with unbounded self-adjoint operators. We want to define when are they when do they commute. And we know that the product operator E1, E2 is just contained in the its adjoint, or the adjoint of E1, E2 is always an extension of E1, E2. But we also know that the adjoint of E1, E2 is also an extension of the product operator E2 adjoint, E1 adjoint. And therefore, since E1 and E2 are self-adjoint operators, of course, they'll drop that and will come up with that equation 6. And if we relate those inclusions, it simply means that E1, E2 is equal to E2, E1. Therefore, the operators E1, E2 commute only if they are operating on the common domain. Therefore, if we have E1, E2 having different domains, then we want our common domain to be the intersection of those two domains. Next, we now come with the construction of the polynomial. And therefore, we want first to come up with the polynomial of degree 1. Therefore, if the polynomial, look at equation 7, which is the first degree polynomial, A1, of course, times I plus A2F, that is polynomial of degree 1 in terms of F. We want to show that this polynomial is self-adjoint using the Motard's result. First, F is invertible by choice. We chose F to be invertible, self-adjoint operator, and by spectral mapping theorem, it is scaled factor. When we scale it, we simply find that also it's the scaled operator A to F will be invertible. Why? Because when there is not an element in the spectrum of F, then it will not be an element in the spectrum of A to F. Therefore, A to F is self-adjoint, is invertible, of course, and self-adjoint. Second, we establish the commutativity of A1I and A2F. Now we know that since these operators have a common domain, and the common domain will be the domain of A2F. Therefore, they will commute to have this result as a lemma that we have just covered. And lastly, if this condition is satisfied, that we choose F such that the domain of the inverse of F is contained in the domain of F, then we will have satisfied the hypothesis by Motard, and therefore we'll have come up with a polynomial P1F, which is a polynomial of degree 1, which is self-adjoint. Therefore, we want to build on that. We have now a P1, which is self-adjoint. We want now to come up with a P2. That means polynomial of degree 2 in F. Therefore, we're just adding one term. And now if we consider that the polynomial P1 plus F2, which is equation 8, P1 plus F2 squared. Therefore, we're now interested in the sum of P1 and A2, F2, which is also just a sum of two operators that are unbounded and also self-adjoint. Now, first thing we have to establish that A2 F2 is invertible, and that is, of course, from a spectral mapping theorem. Have seen that the powers will all, of course, will be invertible, given that F was invertible. Second, you have also set up the condition that E1 and E2, if you choose E1 to be a polynomial of degree 1 and E to be the second time the polynomial of degree 2, be self-adjoint operator, then we easily see that, of course, F2 will be self-adjoint operator. Therefore, if we take E1 to be polynomial of degree 1 and E to be the third term in the polynomial of degree 2, then they will commute so long as we are choosing the domain to be the smallest possible domain, which is the domain of F2 squared, F power 2. Therefore, if this condition is satisfied that the domain of F acting on the inverse of F2 is contained in the domain of F, then the hypothesis by Motard is satisfied, and therefore this P2 will be self-adjoint. Therefore, once we have now come up the result for P1 polynomial of degree 1 and polynomial of degree 2, we can now then come up with a general polynomial, which is a polynomial of degree n. And therefore, this is the result, that when the polynomial, when F is invertible and bounded self-adjoint operator, then you can form a polynomial. This polynomial will be in terms of Fk, which is an unbounded operator, and this polynomial will be bounded and bounded self-adjoint operator, provided that we choose the domain of F power -1 acting on inverse of Fn being contained in the inverse in the domain of Fn. Therefore, that was the key result, and the proof is just based on what we have, based on mathematical induction. Of course, we are looking at the basis, the basis, and the basis is when the degrees is 1. We have just seen in illustration 1 above that the polynomial 1 will be self-adjoint. Therefore, we simply assume that, of course, this could be true for some m, where m is simply a natural number, that this polynomial of degree m is a unbounded self-adjoint operator. Then can we prove that the polynomial of the polynomial of degree m plus 1 is also self-adjoint operator? And that has been also been shown here, that since we take the polynomial of degree 1 to be polynomial of degree m to be the operator E1, of course, is self-adjoint by hypothesis, then the E2 operator E2 to be is also self-adjoint operator, which is the m plus 1 term in a new polynomial of degree m plus 1. Then you come up with two operators E1 and E2, and these two operators are unbounded operator, and they're also self-adjoint. Therefore, they will commute by the lemma that we discussed above. And second, we also discussed that the powers of these operators are invertible, given that F is invertible. Therefore, we have also satisfied that property above. And therefore, since if we can come up with a suitable domain such that the domain of Fm acting on the inverse of the domain of m plus 1 is contained in the domain of F plus 1, then the hypothesis of theorem by Motard will have been satisfied, and therefore the polynomial P plus 1 will be self-adjoint operator. And that is the proof by mathematical induction. And therefore it simply means what? It simply means that our polynomial Pnf, which is a summation from k is equal to 1 to n of Fk, is actually an unbounded self-adjoint operator, provided that it is invertible. And therefore, we're looking at a possible application of this. What are these invertible unbounded operators that are unbounded self-adjoint operators that we're looking at? And an example is a strictly positive self-adjoint operator. That means a strictly unbounded self-adjoint operator is invertible. Therefore, the result actually applies to such kind of operator, unbounded strictly positive adjoint operators. And these are operators unbounded operators whose numerical range is strictly more than 0. Therefore, this result is, has a lot of application, of course, but for now, I've not looked at quite a number of applications, but it has an application in mathematical physics, for quantum mechanics, of course, some other areas in physics which I have not explored so far. I also understand, since it has an application in quantum mechanics, it has also an application in nanoparticles and nanotechnology, because it is also associated with the idea of quantum mechanics. Therefore, that is all about our paper. Those are the key references. And thank you. Of course, I'm open for collaboration, and that is my email. Thank you. Welcome.